today's course outline. Firstly, we will discuss about the introduction part of JK flip-flop, its working, its circuit diagram, truth table, characteristic equation, state diagram and excitation table for it. And then the race around problem in JK flip-flop. And as the solution, we will see S-triggered JK flip-flop and master-slave JK flip-flop. Let's start with introduction. JK flip-flop is named after his inventor known as Jack Kilby. JK flip-flop is similar to that of SR flip-flop where inputs are same as J is equal to S and K is equal to R. But the difference is that JK flip-flop is defined also when both the inputs are 1. The limitation in SR flip-flop, that is when S is equal to R is equal to 1. It is the invalid situation. Here in JK flip-flop it is valid, that is limitation of RS flip-flop is removed here. Here you can see the block diagram of JK flip-flop where we have two inputs named as J and K provided to flip-flop and a clock signal is also there and we have two outputs as Q and Q bar. When J is equal to K is equal to 1, then flip-flop complements its output and it is known as the toggle state. Remaining all inputs and outputs are in the same state as of the RS flip-flop. Here you can see the circuit diagram for JK flip-flop. Here we had used NOR gate with AND gates. You can also draw this with the help of NAND gates only. Here we have two inputs named as J and K provided to AND gate G1 and G2 respectively. And the output of these AND gates were provided to RS flip-flop which is implemented using NOR gate. Working or operation of this flip-flop. Since flip-flop is positive level triggered, so when the clock pulse is high, then only the flip-flop will be in working condition. When both the inputs are 0, the clock pulse has no effect on the output and the output of the flip-flop is the same as its previous value. This is because when both J and K are 0, the output of the respective AND gates becomes 0. When J is equal to 0 and K is equal to 1. When J is equal to 0, the output of the AND gate corresponding to J becomes 0. That is S is equal to 0 and R is equal to 1. Therefore, Q becomes 0. This condition will reset the flip-flop. This represents the reset state of flip-flop. When J is equal to 1 and K is equal to 0. In this situation, the AND gate corresponding to K becomes 0. That is R becomes 0. So, S is equal to 1 and R is equal to 0. Therefore, Q becomes 1. This condition will set the flip-flop and this represents the set state of flip-flop. When J is equal to K is equal to 1. In this situation, the AND gate corresponding to J will be 1. That is S is equal to 1. When Q is equal to 0 and Q bar is equal to 1. So, whenever we have S is equal to 1, the output Qn will be 1. And when Q is equal to 1, then the AND gate corresponding to K, that is R, will be 1. So, the flip-flop's output Qn will be 0. Thus, for Q is equal to 0, we get Qn as 1. And for Q is equal to 1, we get Qn as 0. This situation is known as the toggle state. Now, from the previously explained working of this flip-flop, we can draw the truth table for it. When J is equal to 0 and K is equal to 0. For Q is equal to 0, we get Qn is equal to 0. When Q is equal to 1, we get Qn is equal to 1. When J is equal to 0 and K is equal to 1, for Q is equal to 0, we get Qn is equal to 0. And for Q is equal to 1, we get Qn is equal to 0 again. When J is equal to 1 and K is equal to 0, for Q is equal to 0, we get Qn is equal to 1. And for Q is equal to 1, we get Qn is equal to 1. When J is equal to 1 and K is equal to 1. For Q is equal to 0, we get Qn is equal to 1. When j is equal to 1 and k is equal to 1, for q is equal to 1, we get Qn as 0. When we put these values of truth table in K-map, we get the K-map as shown in the figure. Now, when we solve this K-map, we will get the minimized SOP expression for Qn, that is the next state output, which is as Qn is equal to j q bar plus k bar q, and it is the characteristic equation for this JK flip-flop. Now, we can draw the state diagram for JK flip-flop as shown here. The circle shows the states, the directed lines shows the transitions. Here we can see when current state is 0 and our next state is 0. Then we give input as j is equal to 0 and k is equal to 0, or j is equal to 0 and k is equal to 1. When current state is 0 and next state will be 1, then we have to give input as j is equal to 1 and k is equal to 0, or j is equal to 1 and k is equal to 1. When current state is 1 and our next state will be 0, then we give input that is j is equal to 0 and k is equal to 1, or j is equal to 1 and k is equal to 1. When current state is 1 and next state is 1, then we give input as j is equal to 0 and k is equal to 0, or j is equal to 1 and k is equal to 0. We can also draw the excitation table for this JK flip-flop. An excitation table shows the minimum inputs that are necessary to generate a particular next state when the current state is known. When our current state of flip-flop is 0, then our next state will be either 0 or 1. Let's take first situation when next state is 0. From the truth table, we can see that when we have j is equal to 0 and for any value of k, we get Qn as 0. So we are writing here values for j is equal to 0 and k is equal to x. For next situation when current state is 0 and next state is 1, then for j we have to give 1 and for any value of k we get Qn as 1. Next, when our current state of flip-flop is 1, then our next state will be either 0 or 1. Let's take first situation when next state is 0. From the truth table, we can see that when we have k is equal to 1 and for any value of j, we get Qn as 0. So we are writing here value for j is equal to x and k is equal to 1. For next situation when current state is 1 and next state is 1, then for k we have to give 0 and for any value of j we get Qn as 1. So we are writing here j is equal to x and k is equal to 1. That's all for today's session. We will meet soon with the race around problem in the JK flip-flop. Thank you for watching the video.